and welcome to the afternoon session on Wednesday. Today we have the last lecture of Miguel course, Numerical Relativity, and the Einstein Toolkit. Please, Miguel.
Thank you very much. Can you hear me? Okay, good. If at some point you stop hearing me, just let me know. I'll try to speak up. Right, so let's get started. So the idea for today is to go through the hands-on session that I promised. So I'm flashing here the slide with the instructions. The idea is that, well, I hope that at least people who are interested in following along, have downloaded this image, right? So again, let me just recap a little bit. In principle, this is not necessary for you to use the Einstein Toolkit, right? This is just something that I'm providing because it's easier in such a setting that I give you something that's already working, and then you can immediately start to see the code running. Because otherwise, we would have to go computer by computer to download and compile and so on. So this is just a way for us to sidestep this first step, right? But anyway, okay. So I've given you this virtual image, and this needs to be loaded with VirtualBox, right? So I hope that you've had a chance to install VirtualBox and download the virtual image. Yes. Okay. So then, if we fire up VirtualBox, we just need to, so you import it following this procedure here, okay? And then if you fire up your VirtualBox manager, you should have the image showing here on the left, and you can just start it up, okay? And once you do that, you should be greeted with something like this. So a virtual, the virtual machine, the virtual environment. Does everyone have that? Right. So a virtual image. Yeah. Can I just continue? Okay. So now, if you open a terminal, so you can go here, for instance, in activities, and there's a terminal here, so you can just open it, and this is just like any regular, this is just like any Linux terminal. I've provided for you, so there's a folder here that is called ET, so that's for the Einstein Toolkit, and this is precisely what I've made for you the first few steps that you typically need to do whenever you want to use this. So which is you need to download and then you need to compile. So I've already done that for you, and it's done, and it's inside this folder here, this ET folder. Okay. Now, just so that so yesterday I went very briefly, very quickly through what I call the anatomy of a thorn. So just to give you now the idea with the actual code. So here inside this ET folder, you have a folder which is cactus. Okay, so there we are. And inside this cactus folder, so again, I've already compiled the code for you. You can find the executable here in this exe folder. So this is the cactus executable. Fica melhor assim, se estiver branco. Está melhor. Então, so this is the base. So this is the cactus folder. And then, for instance, inside this folder, there is this arrangements folder, which is the arrangement structure that I was telling you about yesterday. In particular, there is this Einstein exact, the Einstein equation of state, the Einstein evolve. So the Einstein base, where we can find this ADM base, some macros, some hydro base. So the hydro base that I mentioned yesterday. So this is all. So you can, I mean, then you can just explore also at your own leisure here. Now, if you go inside these cactus examples, so arrangements cactus examples, here we can find a bunch of example thorns, and in particular we can find this wave MOL, so method of lines, that I was dissecting yesterday. Okay, so in particular, so if we go here in this in the schedule file, this is the schedule file that I was showing you yesterday. So this is where you can find all these files that I was showing you yesterday during my presentation. Now we can go in detail into this also after the session if you want, but for now, so that this becomes a little bit more interactive, what I would ask you to do is to follow. So I've provided a Jupyter notebook. And I've made it available on my GitHub. So if you go to my GitHub, which you should be able to Google. If you just put GitHub and Zilhão, okay, on Google, Google should tell you where my GitHub is. And so if you go here, I've added the new repository, which I called Zilhão 2024, okay? So here it is. So please go here and download this Jupyter notebook. So there's only one file in this repository, so you can't miss. And I've made available this, I've provided this Jupyter notebook here for you. So please download this to your, so I should specify, inside the virtual image, okay? So do this from inside the virtual environment. You can just, then you can just download this somewhere. Where is it? At some point, this should allow you to, here, yeah, download raw file. So if you go here, maybe I can zoom in a little bit. So there, this allows you to download this notebook file. Okay, can I move along? So you just need to download this somewhere in your virtual machine, and then from your virtual machine, just do as you would for any Jupyter notebook. So just go to that folder and just launch Jupyter notebook. So for instance, for my case, I downloaded this to this documents. Okay, there we go, it's here, you see. And then I just type Jupyter notebook, Jupyter white space notebook. And here it is, okay? I open it. It's a bit small again, let me try to. all on the same page, more or less? Okay, so then let's just follow this along, right? So again, I have some explanation of what we're doing, some very, very brief text. This is just, again, for a very, very basic introduction. This is just setting up the notebook itself. It is very standard. So here I'm explaining the context, right? So this is what I was saying before. So typically, whenever you want to run the toolkit, the very first thing that you need to do is, okay, you go to the web page, you download it, and then you compile it. This takes a long time. It's prone to errors. So this is what's already been done for you in this image. So still, I'm providing here the instructions, so that then if you at home in your own computer you want to actually do the compilation from scratch, there are the instructions here. And if there are any problems, just send me an email. Okay, I'll try to help you out. There's also Qt, which is an analysis tool. Okay, so this is a Python package that that does the analysis of the simulation data. So this is not needed for running the code, but it's very helpful to analyze the corresponding data. And this is available through pip, and you can install it this way. Actually, now there's a new version, so this is probably obsolete. But anyway, for what I'm showing here, this is fine. So this is what we have here. These are the general instructions to build the toolkit. Again, this is the part that we don't need to do right now because it's already done. But the instructions are here so that you can then do this at home from scratch, right? Now, assuming that this is done, and it is in this virtual in this image, I'm just going to store some variables just for convenience. There's some variables, some environment variables for the path to this executable, which is here as I was showing you before. So this is the path to the executable in this particular installation. And so we are ready to do our first run. A good first run to do is the hello world example, which we can do directly from here from the Jupyter Notebook environment. So the way to run this is as any other MPI program, right? So for those of you that have used parallelized MPI programs before, it's exactly the same. So we use MPI run, then the number of processors. So here I'm just specifying 2, but I could say however many I have, and then the executable, which is this this variable that I'm storing here above, and then the parameter file that I want to run. And in this case, I want to run this hello world, and so this is just the path to that parameter file, right? So yeah, this is standard. This is not particular to Cactus. This is standard for any MPI, any program that runs with MPI. So I'm gonna hit it, and there we go. So Cactus run just fine. And it printed, and it did what it should be doing for this example, which is just printing hello world. Okay. So for those who are following along, did you manage to see this text? Okay, sorry. I thought that had been provided. Okay, that's a mistake on my part. Maybe I did that after making the virtual image. But if you just do pip install, should be fine, right? So if you need to do pip install or something like this. So did you manage to see, do you see this? Okay, good. Anyone else struggling, or does anyone else need a bit more time? Okay, now for a slightly more involved or an interesting example, we can run the wave equation. So this is the example that I was showing before, well, that I was showing yesterday. So, for instance, I'm here in this folder. So here I'm just creating. I'm just setting this environmental variable, but you can be whatever. In principle, I think this should work in whatever. I mean, whatever you've downloaded this this Jupyter notebook. So now I'm just making a directory called par files, and changing the directory to this folder I've just created. And now I'm just going to this cell here. Is that better? I can maybe. Good. Okay. So these first cells here, they're not doing anything fancy. I'm just creating the directory, okay, and then just changing to that directory, nothing else. Now this cell, this one here, it's just using this magic, this Jupyter magic commands to write a file, right? So in order for me to, I mean, I could have provided the file for you, but it was just simpler to use this intrinsic magic from the Jupyter notebook. So if I run this cell here, the only thing that will be done is, let me do it. It will write for me this file, this Gaussian rk4.py. Okay, so it wrote for me, it created for me a parameter, this particular parameter file, right? So we can even, so if I go back to the terminal. I can see that I now have this. Let me zoom in. Going back to the terminal, I can see that I now have this folder called par files and this file called Gaussian rk4. This was not there before, right? So this is the thing that we have that the Jupyter notebook just created. Okay, and this is a very simple parameter file just to evolve the simple configuration for the wave equation. Okay, so now we can just run it. So for that, I'm creating a folder called runs, just so that we have a folder where we can store all our outputs. I'm going to that directory, and then I'm running it precisely in the same way that I did for the hello world. Now I just give it. So now I'm just giving it the new parameter file that I've created, right? So I hit it. And there we go. So now we should see this output, and it actually already finished. So it was fast enough. And now we should have a folder called Gaussian rk4 with the corresponding outputs. So again, so now if I go to this runs folder, inside there is this folder Gaussian rk4. This is what we've just run. Okay, so inside there's a little bit of that. Okay, this is the output of the program, the executable that we just ran. Oops. Are we all good? More or less on the same page? Did anyone, so people were following along, did you see this? Did you see this output? Okay. So now we have some output, so now let's do some plotting, okay? So for this particular example, I just tried to keep things as simple as possible. So what we have here is just a bunch of very simple text files in ASCII format. So we can look at how they we can just peek into how they look like. This is their aspect. So there's I can go in a bit more detail, but the basic structure is that there's a column here for the time level, the time iteration. So here we are at 0, so this is the first iteration, and then there's the index for each spatial coordinates. There are the spatial coordinates themselves. So this file here, this is just for the output along the x-axis. So this is what this is. So -15, -14, -13. This is the x-axis, and the y and the z are at 0. And then the last column is the actual data of what here is this u function. And we'll have to go and see what exactly the u function is first. Okay, so now for this sort of output, we can do some visualization very easily with NumPy. So we can do using this gen from text routine. This is very convenient. And one can load the time steps from this output in this way, and this will just plot the first time steps. So there you go. So I'm going back. Let me do it again. So for this u function along the x-axis, I'm loading it up to a bunch of NumPy arrays that I'm calling data. I'm loading it up so I'm extracting the time steps, the available time steps into this data, and then I'm plotting the first time steps as a function of the x coordinate. Okay, so there we go. So we started off with this peak here that then just starts to decrease. So this is just this. It's a very simple evolution. We're all okay so far? Yeah, good. Now we can try and do an animation. So for that, I'm creating this folder called fix, changing directory to that same folder, and then we can create a very simple movie using all these time steps. So what this loop is doing is just to loop in time steps and just then do a snapshot, right? So let's run this. So this first bit here is just looping into all the time steps and doing the corresponding plots. And then I'm doing this. I'm calling ffmpeg to create a GIF, which this is the output, and we can look at the corresponding GIF. There we go. So this was the output that the code wrote for us. So this is a very simple case, and here we're only. We could be doing more involved things, but here we're just looking at the output in one direction. It's really just we're creating a pulse. It's really just dropping and then propagating away, right? This is what you expect for the wave equation. Now going back, so I'm suggesting now some exercises here for that you can then try at home. So you can change the parameters of this of the parameter file that I provided and can compare the output. So for you to change the parameters, you could, for instance, you could either directly change the parameter file that was created, call it something else, and try to run that. Or if you want to keep using this notebook, you could, for instance, come here and change change the parameters. So, for instance, say that you want to change the final iteration for the simulation. You would go here and change this, I don't know, for 400 iterations, okay? Then you would write, say, this Gaussian RK for 2 dot par, and you run this. You run this again, and then you have a new parameter file, and then you can just run it in the exact same way and do the corresponding analysis. So I'll leave this as an exercise for you. Now I have a more interesting example. So, and this actually connects a little bit with what Guilherme has been telling us about, and will probably show us afterwards, which is a static TOV star. So with the Einstein Toolkit, with the Einstein Toolkit, you can just as it is, right? Just straight out of the box, you can simulate. You can do an evolution of these configurations of a TOV star in 3D. Okay. So I'm creating for you here a parameter file. So for a very simple TOV star, it's exactly the same way. So now we should have the parameter file TOV.par. Let me just go back and make sure that, I know, but let me just make sure. So we go here on par files. Wait, it's not here. It's inside runs. Yeah, this is not what I wanted it to be, but fine. Let's keep it here. Actually, I'm going to need to do this somewhere else, because otherwise the rest is not going to work. I probably forgot to run this cell. Don't forget to run this cell. I probably forgot to do that. So let me run this again. Okay, and now let me make sure. There we go. Now we have the parameter. Okay. So again, are we all following along? Are we all more or less on the same step here? So if so, I can go back once again to this simulation directory that I've created, and I can run this parameter file. Hopefully, this takes a little bit longer to run, but it's running. Okay. So this will take a little bit longer. So I'm going to leave it. Is everyone seeing this output? It's running? Okay, so let's give it a few seconds. I'm not sure what I set up. I mean, we can see what was the final iteration. Está a dar, está a funcionar. Tá bom. Okay, where were we at? Ah, okay, okay, good. So mine already finished. It's still running. Give it a little bit more. It should. I mean, if it's running now, you shouldn't find any issues, hopefully. But okay, good. So I hope that so people who are following along, I hope that you're seeing something like this. So if you see this sort of screen, so we've done, means that things went as they should have. And now we can look at the output. So and this time let's look at actual 3D or at least 2D quantities. And for this, let's use this Qubit tool that I was telling you about before. So let's load the corresponding packages. And Qubit is very convenient, so we can start by looking at all the available data. So let me see if this works. Yeah, there we go. So I set up this variable sim to be the simulation directory. Okay, this is where the data was stored. And then I can just, so then this is just the syntax. So inside sim that there will be available GUID functions. So this is the notation, GF, these are the GUID functions. If I say print, it will tell me all the data that's available. So here we can see we have data for the metric. So this is the G, XX, XY, XZ, YY, YZ, ZZ, etc. So this is the metric, the 3 metric. Then the extrinsic curvature, so the KXX, XY, XZ, YY, YZ, etc. The lapse and the density, the pressure, the epsilon, so the energy, the velocity, etc. Okay, so this is stuff that is one-dimensional along the x, along the y, and along the z axis, and then we have also 2-dimensional stuff on the xy plane, the xz plane, the yz plane, and also here in this case I didn't ask for anything that is intrinsically 3-dimensional, so this is a void, it's empty set. Okay, but this is how one should read this sort of output. Now let's look at the data that's available in the z equals 0 plane, so the xy plane. So I'm writing this. I'm creating this variable, this vars2d, to be this the xy available data. And let's look, for instance, to the density. Okay, let's say we want to look at the density of the star. Okay, so this is just the notation. So the density row is inside this fields structure. Let me do this again. There we go. At iteration, so we can access the iteration 0 with this indexation. So the row 0. There are many more iterations. We can look at the available iterations or the available times. So we have until t equals 80. This matches well with what we were seeing in the output of our evolution. And we can also see what's inside now this row 0 quantity. So we see that we have 2 components. So this is related with the refinement levels. So in this case we have two refinement levels. We have the coarsest level with a spacing of 2. So this is the resolution available, and the finer level has resolution 1. Okay. So here I have a bunch of text explaining what we're doing, but let me just move a bit quicker. Let me try to plot the data here at this specific instant, and there we go. So this is I should probably have started here, but in order for this to run so quickly, this is a very low resolution simulation. But it's good enough for this type of tutorial, for this type of visualization. Of course, one wouldn't use such a low resolution for anything serious, but for this purpose, it's fine. And this is a basic contour plot of the density of the star. So there we go. We can also look at scalar reductions, so things that depend on, so for instance, let's say that we want to plot the maximum, so this is again, this is the density of the star at a specific time step, so at t equals 0. But let's say that I want to look at the maximum of the density, okay, and how this behaves as time goes by, okay. So I could use the available time series, and what I would do is this. And if I do that, then there we go. So this is just so the maximum. This is the maximum value of the star, and we see it oscillating a little bit. Okay, so this is not. So this is a configuration that's not fully in equilibrium. Okay, because it's low resolution. It's being perturbed by numerical error. Okay, so you see it's evolving a little bit as time passes. Okay, so here in the x-axis we're plotting. In this case, we're plotting time. Any questions up to now? Okay, so this is this very simple notebook that I provided, so that you can immediately get started and see how you would get started with the simulations and follow along. Now I should also say, of course, in practice, this is not how I interact with the toolkit, right? So I do this for analysis, but not for running the simulations. For running the simulations, I typically, either if I'm using my own laptop or on a cluster environment or whatever, typically I would launch this, I would run these commands. So these are the commands that I use to run the executable. I would run them directly on my terminal, okay, or by using any queuing system if I'm on a cluster system and so on. And then the simulation runs, and then I go back to it, I download it or whatever, and then I can either analyze the data through some Python scripts or through a Jupyter notebook such as this one. So here I'm just doing everything in the same notebook, so all the running and the analysis just again for convenience, okay? Yeah, but so this is it to get one started. Now, what I've also done here, now we're running out of time, but just if you want to then explore at your own leisure at home later, I've also provided. So now, if I go back here to the root directory of this of the virtual machine, I've provided. So we go inside the ET folder, and then I've provided this example data. Okay, so this is some. These are this is a bunch of output of different configurations that I run previously and stored here, so that you can have a look without having to do the simulations yourself. Okay, so in particular, there's a bit more output here in this so I ran a high resolution version of this TOV star, which provides a little bit more data here. So this is this TOV2. I also have some output for the evolution of a wave, a Gaussian packet that evolves just with a plain old wave equation. So there's the output here. You can also have a look. So this is all for this particular one. This is all text files, but you can come and explore this a little bit. And maybe more interestingly, I've given you here some data for the in-spiraling of two black holes. So I'm only providing. This was just in order for the image, for the virtual image not to become huge. I only have here the output for the wave the Psi4, so the wave extracted data. But for instance, we can look at it using nuplot. So let's say that we want to look at, let's say that we want to look at the 2-2 mode extracted at a particular radius. There we go. So this is output that comes straight out of the toolkit and that you can run completely out of the box, okay? So if you want to run, if you, for whatever reason, you want to have the gravitational wave signal for an inspiraling system of two black holes with some given masses and initial momentum, you can just take one of the provided parameter files. You just change the initial data for what you want. You let it evolve, and you can get the signal, the gravitational wave signal, as we are in a very straightforward way. So this is such a signal. Okay. Now, just before we finish, let me give you also a taste of visualization with Visit. So I've installed, so there's a program for visualization that's called Visit. You can find, I mean, you can find it online. So if you just write Visit visualization, you go immediately to the home page, and there's the instructions to download and install. It's usually very straightforward. Again, I've already done this in this VirtualBox image. So if here I go and I launch it, Visit already knows how to read Einstein Toolkit or carpet data, and so let me just give you just a brief idea of how you would go, what you would do to look at some of these data. For instance, here again, I'm providing the density. This is just the density profile for a star, like the one that I was evolving before, like the ones that Miguel has been telling us about. So here I need to tell it that this is carpet data. Okay, I'm picking the file that I want. So now let's say that I want to look at some contour images. This is a 3D data. Okay, this is not very helpful. Let's slice it. So let me do 3 slice. Let's see if this works. There we go. Okay, so you see. So this is the density. So you can think of this as the density of the star, and I'm doing like slices along the three planes, and this is the value. Okay, this is again, it's very straightforward to do with this application with Visit, and then you can manipulate this to animations, do a bunch of cool things. In this case, I'm again, for reasons of space, I didn't want to have the image of the VirtualBox image. I didn't want to have it too large. I mean, it's already large enough. So this is just one time step. Okay. So this. No, actually, no. I have a few time steps. No, I don't. It's not a long evolution, but I did manage to store a few of them. Okay. Yeah. So that there's actually some evolution that we can see. But it's fairly trivial because this is relatively short. But let's see. So here, if we hit play, there's not much that's happening. I mean, we can see that it's oscillating a little bit, but not that much. Okay, so we are almost out of time, and Guilherme is talking afterwards. So I think I will stop here and take any questions that you may have, or if you're struggling with anything. So.
question or comment? Nobody? Well, if you have no questions and no comments, I'd like, in the name of the organizing committee, thanks Miguel for his very nice short course. I think the students agree with me. It was really interesting principle for the young ones. So let's thank the speaker again.